Okay, let's unpack this seismic shift in the world of physics, because this truly is a challenge to fundamental laws. I mean, for centuries, we had Newtonian mechanics describing gravity perfectly on Earth.
Right, for everything we could see and touch.
Exactly. Then Einstein's general relativity expanded that, showing gravity as the curvature of space-time. But now you have researchers out of Sejong University in South Korea publishing in the Astrophysical Journal, and they're basically saying that neither framework really holds up in certain specific cosmic scenarios.
What's particularly fascinating here is the subject of their study. They aren't looking at, exotic black holes or the moment of the Big Bang.
Nothing that extreme.
No, they're looking at something relatively common in our galactic neighborhood.
Oh.
Wide binary star systems.
So just to be clear, that's simply pairs of stars orbiting a common center of mass.
That's it. But the key is that they're separated by enormous distances, which leads to these very, very weak gravitational interactions between them.
And they had a huge data set to work with for this, I assume. You'd need one for a claim this big.
Oh, precisely. They analyzed observational data from the European Space Agency's Gaia Space Telescope, which is cataloging billions of celestial objects. Their sample focused on over 26,500 wide binary systems just within 650 light-years of Earth.
26,500. Okay, so that's a tremendously robust sample size. That gives their findings some significant weight.
It does. And what they found is that at a very specific ultra-low level of acceleration, physics as we know it seems to just break down. That's the critical threshold.
Right. Tell me about that threshold.
That's the core discovery. When these stars experience these ultra-low accelerations, and we're talking about tiny, tiny movements, around 0.1 nanometers per second squared.
Which is almost nothing.
Almost nothing. Their observed orbital motion deviated significantly by 30 to 40% from what general relativity and Newtonian gravity predicted.
30 to 40%, that's colossal in physics. That's not a rounding error. It suggests that gravity is somehow stronger, or at least operating differently, than we predicted at these vast cosmic distances.
Yeah, where the gravitational fields are ultra weak.
It feels like this has to be some kind of statistical error, or a bias, or an experimental problem. How sure are the researchers that they've ruled out things like that?
Well, that's the crucial point of the study, and it's why it's generating so much discussion. The researchers spent a considerable amount of time modeling every known source of error, including the possible influence of stray interstellar gas or, unseen companions.
So they tried to explain it away with normal physics.
They did. And their conclusion stands that the deviation is statistically significant and cannot be easily explained away by standard modeling. And this points very strongly to a threshold effect.
A threshold effect, meaning standard physics works perfectly above a certain acceleration level, but once you drop below that, the rules just change.
Exactly. At higher, more typical accelerations, say, when the stars are closer or moving faster, standard physics holds true, the observations align perfectly. But once you dip below that specific low acceleration threshold, gravity appears to exert a greater influence than predicted by the classical inverse square law.
So if Newton and Einstein are failing us at this ultra-low end of the spectrum, where does this deviation lead us? I mean, it sounds like we need to revise the entire textbook.
This is where we bring in something called Modified Newtonian Dynamics, or MOND.
MOND.
Yeah. MOND was proposed by a physicist named Mordechai Milgrom back in the 1980s. It's essentially a revised gravitational framework that suggests a slight modification to the law of inertia, or gravity itself, specifically in weak gravitational fields.
Okay, but usually we invoke dark matter to solve these kinds of gravitational mysteries, like the galaxy rotation curve problem, where galaxies spin too fast. Why bother with MOND if we already have dark matter theory?
That's the core intellectual conflict in modern cosmology. The traditional cold dark matter, or CDM model, solves that galaxy rotation problem by positing these huge, invisible halos of mass.
Right, just stuff we can't see that adds gravity.
Exactly. MOND, however, argues that you don't need this invisible mass, you just need to tweak the equation for how gravity behaves when it's extremely weak. And this new study on binary stars provides some of the strongest empirical support for a MOND-like effect we've ever observed, especially this close to home, in our local galactic neighborhood.
Which makes it difficult for the CDM proponents to just dismiss it.
Very difficult.
Wait, so if MOND is so elegant in explaining these phenomena, why are cosmologists still spending billions of dollars building detectors to find dark matter particles? Shouldn't we just, I don't know, dump CDM?
Well, it's not that simple, unfortunately.
Yeah.
General relativity explains almost everything else. the cosmic microwave background, gravitational lensing, black holes. MOND is excellent at galactic scales and maybe these ultra-weak binary scales, but it really struggles with large-scale cosmology, like explaining the dynamics of entire galaxy clusters.
Ah, so the implication, as you pointed out, is that we might need some kind of sophisticated hybrid model.
That's where this is heading, a model where Einstein's general relativity governs the strong and intermediate fields, but MOND takes over for these ultra-low acceleration environments. And that forces a complete paradigm shift.
And if we connect this to the bigger picture, a shift in our understanding of fundamental gravity has profound implications for dark matter and dark energy, doesn't it?
It absolutely does. If MOND can explain some of these gravitational anomalies without invoking dark matter, it significantly challenges the cold dark matter model. It means the 85% of the universe we can't see might be less about missing mass and more about missing physics.
That's the ultimate aha moment in physics, finding out the universe is governed by something a bit more nuanced than we thought.